even if you're not stoked for more organic chemistry, let's put our smiley faces on. Yay! All right. Hey, everybody. We quick turnaround from cars there, so I figured let's get off to a little bit of a slower start. We'll kind of ease into things. I've got a poll here. It doesn't really matter if you were or were not in the previous OChem session, but it looks like a fair amount of us were. So I'm going to change some of the ways that I would normally teach this to maybe build in some of the principles that we learned from earlier tonight. If you said, no, I wasn't here, you're going to be just fine. Don't worry about it. We're just going to ask some extra questions that kind of pertain more to some of the content from the earlier OChem session. If you do want to watch that OChem session, remember that this and all channel sessions are going to be archived. You guys will find those on your channel starting about 48 hours from right now. So what we're doing today are ideas that are separate from the OChem that we did earlier tonight. And that's why you don't need to have been to that previous OChem session to get along tonight. But what we are going to recognize, especially that 75% of you who were in OChem earlier tonight, is that there's a lot of overlap. And those of you who didn't go to OChem earlier, when you do end up watching that channel session, it goes both ways. It's a bi-conditional, right? The stuff we learn here will help in that session and vice versa. And what we're going to see is that right off the bat, we've got 5 learning goals here again today. But let's look at the first one. We want to recognize key players in reactions. Let's see if we can draw some connections to some of the ideas that we saw earlier in class. One second, gang. There we go. Let's see, and we're gonna be getting that recap document for the last session in the pod in the lower right. I saw some of you guys asking about that because again we did have a quick turnaround. Looking at this is an overall reaction mechanism. It's not 3 individual reactions. We have a starting reactant and a ending product. And you guys tell me, what do you notice as the big difference between our starting product and our ending reactant? I said that backwards, but you guys know what I meant. Our starting reactant, our ending product. It lost that carbonyl. Yeah, we converted that carboxyl down to an alcohol, and if we want to use the super snazzy language of chemistry, we might say, well, the number of bonds to oxygen, they were reduced. What do we call this? Reduction. Yeah, we got a great example of reduction happening right here. In fact, again, if this is your first time with us tonight, or you are returning from earlier, I notice a great reducing reagent. I see a great reducing reagent right here in step 2. Lithium aluminum hydride. How can I recognize that guy as a great reducing reagent? What's the trick, the mnemonic to this? Lots of H's. Lots of H's. So put yourself in the mind of a chemist for 1 second. It's a scary place. We won't spend any more time there than 1 second, right? But I'm a chemist and I'm saying, man, I would really like to reduce down that oxygen so I could get rid of that carbonyl in my final product, but there's a big problem, this ketone. I don't want to get rid of that ketone, I want to keep that ketone. In fact, if I react a ketone with lithium aluminum hydride, what will happen to that poor little ketone? He'll be reduced as well. He'll be, bye-bye. Yeah, he'll be reduced down to a secondary alcohol, Stefan. Exactly. So one of the ideas we talked about in the first OChem lesson tonight, and again, this is a good shout out if you haven't seen that one to the utility of that lesson, is we can use an alcohol, ethylene glycol here, to protect that ketone group. And notice by converting that ketone group into a, what kind of functional group was this, gang? We turned our ketone into a, it's got 2 OR groups. You guys are close, close. Started with a ketone, though, not an aldehyde. Yeah, we turned it into a ketal, and it's very close to a geminal diol, gang, only we have 2 OR groups instead of 2 OH groups. We turned our ketone into a ketal. That ketal was then protected until the very end when we turned our ketal back into a ketone. So you see here a lot of great overlap with some of the ideas that we talked about earlier. Now, again, Eli's telling me we got some questions about that protecting mechanism. I want to point out that is covered in detail in the first, in the other, the twin to this session, the organic chemistry reactions part 2 session. So for now, I just want to point out what we see here are a lot of examples of nucleophiles reacting with electrophiles, oxidation and reduction, and thinking about the solvents and the reagents that are involved. That is what we mean by recognizing the key players in reactions. Dug a little deeper into this than we normally would, but these are the ideas that we're looking at in this lesson: solvents, nucleophiles and electrophiles, and leaving groups. Great. Let's take a look at some of these ideas. So thinking big picture here, a nucleophile, what is the property that we're looking for when we want to identify a nucleophile, ladies and gentlemen? What is, like, at a glance, our key for spotting a nucleophile? Yeah, they got electrons. They are generally an electronegative atom because that pulls electron density towards itself. They have electrons. Remember, they are nucleus loving, so they want to donate electrons overall. We can spot at a glance, those guys are clearly nucleophiles. They've got a negative charge right on them, right? So anions make for great nucleophiles. What about these guys? Not as easy to spot unless you're trained for it, but we're doing that right now. So how can we spot these guys as great nucleophiles? Yeah, those pi bonds. We got lots of electron density wrapped up in a small place. We know electrons, why they're negatively charged, they want to get away from each other. So if I'm forcing them into a small place, if I have a lot of electron density bound up right there, these guys are often going to undergo reactions that will help them spread that electron density around via reacting with other atoms or molecules. Nice. Pi bonds. Cool. Finally, we take a look at one more example. These guys are all pretty good nucleophiles. Why? How can I recognize at a glance? Lone pairs. Lone pairs. Yeah, lone pairs, right? Now, we want to be able to compare the strength of nucleophiles, and that's something we're going to be talking about in just a minute. But I want to point out as a general rule of thumb, ladies and gentlemen, bases are nucleophiles. Nucleophiles are bases. There's often this dichotomy drawn between these two topics, and it just confused the crap out of me when I was studying this as a student. So I want to point out here, what do bases want? In general, if I am a Bronsted-Lowry base, what am I looking for? I'm looking for a proton. Yeah. What charge do protons have? Positive. So notice that bases and nucleophiles, they want exactly the same thing. Bases are nucleophiles. Nucleophiles are bases. What determines whether we call something a base or a nucleophile is how it reacts in solution. Good bases, why they want protons. Good nucleophiles, they generally want positively charged carbon atoms, but either way they're seeking out a positive charge. So the same things that make a good base are going to make a good nucleophile. There's a big caveat here, but good nucleophiles are not necessarily good bases. In fact, take a look at the Br- anion. What could you guys tell me about the, let's say, the relative stability of Br- in solution? It's pretty stable. So is this guy going to go around snatching protons off of molecules? No, he's not going to be a very good base because he's not going to behave in that way. However, if this guy sees a nicely exposed carbocation, boy, he's going to be all over that, right? He's going to jump on it. So this guy may not make a great base because he doesn't behave in that way, but he still will attack a positive charge if one presents itself. That's the key idea here. Bases and nucleophiles, they're really the same thing. It just depends on how they behave in solution. You see some things that aren't necessarily going to attack protons. They still will attack carbocations or those kinds of things. And that's what makes them good nucleophiles overall. Now, on the other side of the scenario, we've got electrophiles. Electrophiles are electron-loving species, right? Generally, what are we looking for that are going to help us identify an electrophile? These guys got some kind of positive charge. They need electrons to fill their lack of negative charge. Feed me negative charge. More positive equals better electrophile. So let's play a game here. I've got a carbocation and I've got bromomethane. Both of these guys are electrophiles. Both of them are pretty good electrophiles. Notice bromomethane, very little steric hindrance on a molecule like that guy. Maybe that'll come up later on today. However, what we're going to see is that the carbocation is the better electrophile. Why? Yeah, it's got a full positive charge. That carbocation he's just dying for some negative charge, right? We're not talking about a sharing situation, an unequal sharing situation. We're talking about the magnitude of charge makes it a better overall electrophile. Cool. Continuing this game, I've got acetone and isopropanol. Acetone and isopropanol. Now, what we're seeing here is that acetone and isopropanol, again, about the same amount of hindrance. You might say acetone's got a bit less hindrance, and you'd be right. But there's another reason why acetone's a better electrophile as well. Let me put it this way. Why might the carbon here have more positive charge than the carbon on the right? Why might acetone's carbon have even more positive charge? Sure. Yeah, there's two ways of saying kind of the same thing here, right? Those of you who favor the inductive view will say, well, this guy's got a lot of bonds to oxygen. That's going to pull a lot of electron density away from that carbonyl carbon. Those of you who favor resonance are going to say, well, Tyler, there's this resonance structure where we're going to push electron density up onto oxygen, and that leaves a full positive charge on carbon. I want you guys to recognize that's actually two different ways of saying exactly the same thing, right? So what we're seeing here is acetone simply, again, has more positive charge on that carbonyl carbon. There's lots of different ways of saying that, but at the end of the day, what we're seeing is this fundamental trend. More positive means more reactive, better electrophile overall. Beautiful work here. Nice. So let's talk next about what happens when a nucleophile does attack an electrophile. Generally, we're going to be kicking off a leaving group. Now, starting question for you guys, we call this a leaving group because it leaves, right? But bromine, we know what kind of a reactant is bromine overall. Bromide, technically, once I kick him off of there. He is crappy. He is a halogen, but he's also a nucleophile. Yeah, he's a crappy halogen nucleophile if you want the full picture of bromine, right? So, Hannah, you're right. He could just attack again, right? What we're seeing anytime that we have nucleophilic attack is that the leaving group is itself a nucleophile. However, let's repeat an idea we just talked about. What do you guys know about the relative stability of bromine in solution? The bromide ion specifically. Yeah, it's very stable. It's very good. It's very highly stable. It does depend on the solution. We'll get into some of those factors later on. But in the kind of solutions that are going to be favorable to SN2 reactions of this type, bromine is going to be very stable. Bromine's got an octet. He's a big fat anion. Generally, anions towards the bottom of the periodic table are quite stable. So what we're going to see is he gets kicked off and stays there. The point I want to make for now, gang, is when we look at these reactions, we're looking at a battle between two nucleophiles. We're assuming generally that my incoming nucleophile is stronger than my outgoing nucleophile. The thing that we want to keep in mind is that the stronger nucleophile will win, and we call it the nucleophile. The weaker nucleophile will lose, and we generally call it the leaving group, just so that we can have some kind of difference between the terms used here. Great. Now, take a look at this guy here. That looks like a wonderful nucleophile. You might answer some of the questions I see coming through in chat. Well, a wonderful leaving group, rather. Why would this phosphate anion be super duper stable in solution? Resonance, yeah. So if big anions are stable because they can spread electron density out over a bigger atomic radius, then a big ol' anion like that phosphate anion, he's going to be super stable in solution because he can spread that electron density out even more. Christopher, you want me to really blow your mind, dude? I'll try, right? Why is resonance the answer every single time in organic chemistry, right? What are we doing in resonance? Well, we're spreading electron charges around. Why would we want to spread negative charge around? Why would we stabilize a molecule by moving electron charge out over a greater surface area? Less reactive, lowers the energy. Why? What is the fundamental physics principle that says if I take negative charges and separate them in space, I lower the energy? Repel, entropy, stability. There's one famous dead guy that I'm looking for here. Coulomb. Coulomb's law. Coulomb's law says that if we can spread electron density around in space, it will cause less energy, thereby stabilizing the molecule, and that means favorable reaction. Now, how about this? Why would a nucleophile who's negatively charged want to attack an electrophile who is negatively charged in the first place? What is it about negative and positive charges that make them want to react with each other? Yeah, they're opposite charges. They attract. And when I bring a positive charge and a negative charge closer together, what happens to the overall energy of the system according to Coulomb's law? We're going to decrease the energy according to Coulomb's law, right? Why is it that polar molecules are stable in polar solutions? Because we have positive and negative charges attracting to each other. Why is it that things that can H-bond have higher boiling points? Because they have positive and negative charges that attract to each other. If you guys have never made this connection, and I understand, because when I learned organic chemistry, it was fact, memorize all this stuff. No. At the heart of chemistry is Coulomb's law, the idea that like charges repel and opposite charges attract. And I would posit that we can explain literally every single concept on the MCAT if we're looking for where are the positive charges, where are the negative charges, how are we minimizing repulsions and maximizing attractions. So I get it that you guys say, man, resonance is everywhere, right? The key idea here is it's all explainable by Coulomb's law. And in fact, we're going to see that idea come up again and again. That's why I wanted to take a little, admittedly, a little detour on that. But it is just, it's so beautiful to me how everything works out according to this idea of attraction. Now, let's continue right along with this. We said in the last organic chemistry lesson, OR groups in general are terrible leaving groups. Here we have an OR group, but what we've done is we've gone ahead and protonated it. Now, let me ask two related questions. How can I tell that this molecule overall is highly unstable? What's the signpost that says, bro, that's not a super stable? Yeah, positive O, right? That means that this molecule is highly reactive. Now, on the other hand, look at that charge. On the other hand, if I kick this guy off, what kind of a molecule am I going to have? I'm going to have an alcohol, which, as Tadell points out, is super stable. So if OR groups are terrible leaving groups, protonated OR groups all of a sudden become excellent leaving groups. Our nucleophile comes in, our stabilized leaving group leaves, and notice OR groups, water, and ROR groups, these guys all make great leaving groups because they're all so stable on their own in polar solutions. Sweet. Finally, I'm wondering if anybody recognizes this ion. It's a big, scary-looking guy, but it's also one that's good to just know at a glance. We talked about it in the last OChem session. This is a tosylate anion. Yeah, the unanionic version would be tosylene. This is a tosylate anion. It is the MCAT's shorthand for super awesome leaving group. And you can see it's a super awesome leaving group because it's there's resonance, there's inductive effect. We're going to take that negative charge and we're going to be able to spread that negative charge out across this whole freaking surface area. Coulomb would be very happy with how much spreading we get of that negative charge. Nice, nice, nice. Now, we take a look at the other side of the equation. Look at this. If protonated OR groups are great leaving groups, here we have just a regular old OR group. This guy's a terrible leaving group. And in fact, if you were a little bit fuzzy on why, let's take a look at why, right? I'm going to kick that guy off, and I'm going to get a straight up OR group. Now, in terms of basicity, OR, OH, what do you guys know about the basicity of a molecule like OH or OR? Yeah, not just strong, but these are the literal definition of a strong base, right? These guys, by definition, want positive charge. What does that tell me about their nucleophilicity as well? Right, because bases are nucleophiles, nucleophiles are bases. If OR is by definition a strong base, it's also by definition a strong nucleophile. So if we view these reactions as a battle between nucleophiles, here, guess what? Our nucleophile, he's going to lose. Bro ain't even got a negative charge. Look at this. We've got a nucleophile with a lone pair versus an OR group with a negative charge. Come on, man. Not even a competition. Sorry, dude. Thanks for playing. I'm sure you're a nice guy. Right? But that's just not going to cut it for us. Right? What about if OR groups are bad leaving groups? What about straight up R groups? Here we have just a straight up R group. Not an oxygen to be found. Terrible. Terrible, right? And again, you could think about it like follows. What if we did kick that guy off? Then we'd have a carbanion. Now, if OH minus is a strong base, carbanions are even stronger bases because we know oxygen, he can carry a negative charge and he'll be all right. He's not going to be happy about it, but we see that. Carbon hates having negative charges. We rarely see carbanions in chemistry, only under very special circumstances. So we're almost never going to kick off an R group. And finally, you might say, protons, Tyler, protons seem like great leaving groups. Aren't we pulling off protons all the time? But remember, gang, if we're going to replace that hydrogen with a different nucleophile, what kind of charge is he going to carry with him? In fact, each time we've kicked off our leaving group here, what kind of charge has it carried? Yeah. We're not plucking off a measly little proton here, which happens all the time. We're trying to displace a hydride anion, and that's going to be a terrible leaving group, right? Now notice, what do all of these have in common? They all have negative charges. They're all amazing bases, and therefore they are all amazing nucleophiles. They're not going to want to get kicked off overall. They're not going to want to get kicked off. Sure, so Hannah, we could have redox reactions where we're going to be passing along electrons. That's a different topic for a different day. That's not nucleophilic attack. Now we're talking about redox. Okay? Now what we have here are a couple of questions for you guys to practice with. What we're going to do is assign these questions for homework. Again, these questions have been scattered throughout this lesson so that you have some correspondency between the question topic and the learning goal itself. But Let's move on to our second learning goal here, distinguishing between different kinds of reaction conditions, something that was brought up in the chat already. So you guys are sort of presaging the ideas that we're talking about. Now, so some build up to this. Methanol is a protic solvent. What does that mean to say it's protic? It has protons. It can protonate things. Yeah. Now, I want to point out, like a little bit more specifically, not just hydrogens, but OH, not just OH rather, H bonding in general. H bonding is going to be the thing to look for vis-a-vis protic solvents. If we're looking for a protic solvent, some kind of H bonding mechanism. And we're going to see what role that plays in just a moment here. But then what would make this aprotic? You see this is ethoxide, it's an ether. Nice. Yeah, home in on what Emily has said there. It doesn't form H bonds. Again, it's not just has hydrogens or lacks hydrogens. Ethoxide definitely has hydrogens, right? It's got carbons with hydrogens all over it. But what we're looking at here, and to answer Sion's question, we're looking at the difference between H bonding, then protic, no H bonding, then aprotic. Okay? Finally, we have an acidic solution as well, and we can think about the role that acidic solutions play. In fact, this is a repeat of what we've already talked about. Here I have an OR group. It's kind of a fancy OR group, right? I have O bound to R, and then that R is bound to the other O. But what do you guys know about OR groups in terms of leaving groups? Are they good leaving groups or not? They're terrible leaving groups. In fact, some of you guys asked about this protective mechanism earlier. What we did was we replaced our ketone group with this ketal group because that makes it a terrible reactant. It's not a good leaving group. However, gang, if I put this in acidic solution, I will therefore protonate this bad boy. And what do you guys know about protonated OR groups in terms of leaving groupness? If I can just make up a term. In terms of their leaving groupness. Yeah, they're great leaving groups. So you see the sort of the motivating idea about these reaction conditions. I can take a terrible leaving group and I can turn it into an excellent leaving group simply by putting it in the right overall circumstances. Nice work here, gang. Looking good. Let's keep going and dig into these ideas a little bit more detailed here. What kind of reactants, what kind of solvents, rather, are we looking at here? Acetic acid, water, and ammonia. These are protic. Yeah, because they can H bond. All of them can H bond. That makes them protic. What we're going to look at here, you see the trend there. You see the trend there. In polar protic solvents, nucleophilicity increases down the periodic table. And let's take a look at why this might be. What we're saying here is that if I wanted to compare somebody like bromine, which we'll do in green because he's good, versus somebody like fluorine, which we'll do in red because he's a bad nucleophile, again, this is the trend for polar protic solvents. Now, I want to know why, and we're gonna build that idea right now. First off, think about hydrogen fluoride or hydrogen bromide, right? Both of these in solution, what are they going to do? What are these guys going to do in solution? They're going to dissociate. Yeah, they're going to dissociate. They are acids, and that's what's going to lead us to bromine or fluorine in solution. Now, let me ask you guys this. If we have a polar protic solvent, what we're going to see is that these guys are stabilized to some degree by that polar protic solvent. So what we're seeing here, bromine is going to be somewhat stabilized by the polar protic solvent versus fluorine. Now, I want you guys to take a look at this part here very carefully, right? I said that a base is a nucleophile is a base. The difference just depends on how they act in solution. If I want to see fluorine act like a base, what does he need to attack on my molecule here? If he wants to act like a base, to act like a base, he's going to attack this proton over here. Yeah, this would be acting like a base. We'll call it B for base. What if he wanted to act like a nucleophile? Where would he attack if he wanted to act like a nucleophile? Yeah, if he wanted to act like a nucleophile, he would attack that carbonyl carbon, right? So what we're seeing is he could do either one. He could act like a base or he could act like a nucleophile. To say that fluorine is a bad nucleophile, all that means is he would much rather act like a base in this circumstance. And let me ask you a follow-up question. How can you guys tell that fluorine is going to be more basic than bromine in the first place? Yeah, he's more electronegative. He's this small, angry little atom. So what we're seeing is that fluorine is, in this case, we're saying he's a bad nucleophile. All that means is he's more likely to act like a base in the given reaction conditions. He's more likely to deprotonate this molecule, returning to his original HF state, versus bromine. Bromine, specifically because he is less reactive, bromine in this same circumstance would be much more likely to attack the carbonyl carbon itself. Great. Now, if we look in an aprotic, a polar aprotic solvent, we see that that trend exactly reverses. Nucleophilicity increases up the periodic table. And the reason why is very simple, right? If I don't have protons around, can I act like a base? No, right? So remember, the question is not really, am I a better nucleophile? Am I a better base? The question is, am I going to attack a proton, in which case I'm acting like a base, or am I going to attack an electrophile, in which case I'm acting like a nucleophile? If there are no protons around, as in an aprotic solvent, everybody has to act like a nucleophile, in which case the most reactive species wins. Fluorine, he says, dude, I'd like to act like a base. There aren't any protons around, so I guess I'd better attack attack an electrophile instead, right? Finally, let's think about in nonpolar solvents. It says this is a big problem for nucleophiles and electrophiles both. Why would nonpolar solvents not be good for any reaction involving nucleophiles or electrophiles? Yeah, there's a slogan, right? Like dissolves like. When we talk about nucleophiles and electrophiles, we're talking about charged species, we're talking about polar species. They're not going to dissolve in a nonpolar solvent. So you'll often see this distinction between polar protic and polar aprotic. And if you're like me, I wondered, well, wait a minute, what about nonpolar solvents? They don't make sense. You'll never see them in the context of an SN1 or SN2 reaction, a nucleophilic substitution reaction, because we need a polar solvent of some kind for the reaction to occur. Yeah, Emily, I was a struggling organic chemistry student myself once, so I'd like to think maybe I got a little insight into what it's like. Okay. Now, I want to talk about Lewis acids and Lewis bases and acids and bases in general, because we've seen that that is a factor that can be varied and it has huge impacts on our reaction. We haven't talked about Lewis acids and bases yet, right? But what makes, for example, tetrahydrofuran a Lewis base? He's got that lone pair of electrons, right? Now, you might be seeing a little bit of tie-in to nucleophilicity and electrophilicity in general. We'll touch on that again in just a little bit. But Lewis bases are electron donors. Lewis acids are electron acceptors. You see these guys are obviously going to have a nice little reaction there where the Lewis base gives electrons, the Lewis acid accepts electrons. We'll talk more about the significance of Lewis acids and bases in a little bit. The more familiar example is Bronsted acids and Bronsted bases. Here we have a proton donor and a proton acceptor. But let me ask you guys this. Could I call pyridine rather? Is he also acting as a Lewis base in this reaction? Take a look at this reaction here. That proton comes across. He's a proton acceptor for sure. Oh, but he's definitely also acting as an electron donor, right? How about acetic acid? Take a look here. Is that proton accepting an electron pair? Yes. So if you've ever wondered about this, and I know I was a chemistry major, I wondered about this all the time. Let me draw you guys a little diagram that I think helps explain this. If we look at the world of acid-base chemistry, Bronsted-Lowry is the go-to. Proton donors, proton acceptors. It's super famous. However, if you look at the world of Lewis acid-base chemistry, what we're going to see is that all Bronsted-Lowry bases are within the realm of Lewis bases. All Bronsted-Lowry acids are also Lewis acids as well. The idea here, gang, is that Lewis acid-base chemistry is a more general term of Bronsted-Lowry acid-base chemistry, and we'll see yet one more tie-in to this before this night is over, right? The idea here is, again, two different definitions at their heart are saying the same thing. So let's take a look at reaction conditions and specifically acidity strength. If we go from left to right here, what we're seeing is that the acids are getting more and more acidic from left to right. Why? How might you guys recognize these guys as getting more and more acidic from left to right? The pKa values are a great illustration there, Tidell. Yeah. They're becoming more and more charged as we go. Absolutely. We've got a molecule that's non-polar. We've got some lone pairs. We've got water. We've got a molecule that's polar, that H bonds. We've got a molecule that's straight up positive charged. Absolutely. So that's one way to look at this. Another way to look at this is to look at the conjugate base. Because, gang, if I am a more reactive acid, what does that tell me about the stability of my conjugate base? The more reactive my acid, yeah, the more stable the conjugate base, right? So if we look at these conjugate bases, notice that the conjugate base of water, of my hydronium cation that is water, right? By contrast, the conjugate base of my ethane molecule is a carbanion, which we already said is extremely reactive, right? So what we see is as the acid gets more acidic, at the same time, the conjugate base gets less and less reactive, more and more stable along the way. Three different ways. We looked at the data, the pKa's, we looked at the stability of the acid, we looked at the stability of the conjugate base. Be comfortable with all of these ideas. And also, let's just take a moment and appreciate how pretty those arrows are. I kind of want that exact color scheme for my Honda Element. Like, if I could get that painted on there, that would be outstanding. Again, a couple of questions here that you guys can practice with after class. What I want to do now is move into our third learning goal, which is redox reactions, right? What you guys who came to the first OChem lesson are going to find is that this is very much a review of the other OChem lesson. What those of you who haven't yet been to that other OChem lesson are going to find is that that lesson will then be a review of this. So let's go through this as a brief review here. How can I recognize that these guys are becoming more and more oxidized as time goes on, or as the reaction progresses here? More oxygens. Yeah. How could I recognize that these guys here and here are great oxidizing reagents? Lots of oxygen. Yeah. Technically, the oxygen is pulling electron density off of the transition metal, so that we have, for example, manganese with a +7 charge. That makes this an extremely reactive oxidizing reagent. But for us, the O's give it away. We are pulling, we have electrons, we have lots of oxygens. That makes for a great oxidizing reagent. Cool. Right on. Now, when we look at this overall schema, right, what we're seeing is if I take my strongest oxidizing reagent and I react it with ethanol in the first place, why, then I can just jump straight over to the acetic acid side of things here. So again, you have to be careful of the reagents that you're using, and that feeds back to our previous learning goal, the reaction conditions and the solvents that are being used. But as a rule of thumb for the MCAT, more oxygens, more oxidized overall. Let's take a look at some specific reactions involving this. Now again, I'm telling you guys, what we're going to see are some reactions that involve forming bonds to oxygen, right? That's what makes this oxidation. And let me ask you, what part of my reactant molecule here is the most susceptible to forming bonds with oxygen? Yeah, that double bond. Let's take a reality check here. Let's jump out of the world of mnemonics and tricks and think in the real world, what does it mean to be oxidized? The general chemistry definition, the chemistry teacher sanctioned version of oxidation. Losing electrons. So if we want to think about what part of this molecule is most likely to lose electrons, why, there he is. It's the guy with the pi bond, the guy with extra electrons. He's going to be extra susceptible to oxidation, right? So what we're going to see is that bond is where the attack occurs. And notice what we've done is here we've basically broken the reactant in half and made some bonds to oxygen along the way. We've got acetone and acetaldehyde here in this oxidative cleavage mechanism. Cool. Right on. Now again, you guys might guess what we're going to see here. Let me point out that what we're going to use this time is a bit weaker of an oxidant. So what kind of an alternative product might we get? Instead of breaking that bond all the way in half, what kind of a compromise or bridge or middleman might we get? Yeah, let's get a triangle. Let's get an epoxide. Here we have a little bit weaker oxidizing reagent. So instead of breaking that bond all the way in half, instead we add a bond to oxygen to each. We don't oxidize carbon nearly as much. We sort of stop halfway, right? Finally, take a look at glycol formation and cleavage. The fact that we're forming a glycol tells me what kind of a functional group are we adding. We're going to add an alcohol, right? What we're going to do here is we're going to add an alcohol to each of these groups. Osmium tetroxide is a great way to do this. We're not going to go into the mechanism of this in this class, but if you do look it up on Wikipedia or something, you'll see the structure of osmium tetroxide really plays nicely with this. Now, let me point out, gang, a glycol is a special kind of diol where the oxygens are on adjacent carbons. Again, what we're doing here is we are oxidizing the group that's most susceptible to attack. We can then further oxidize this by reacting it with a further oxidizing agent. And notice here, again, all of our oxidizing reagents, at least all these strong ones, they all have oxygen in them, as Nikolai is pointing out. We're just forming more and more bonds to oxygen. That will help you memorize these reaction schema overall. Great. Let's look at the reduction side of the picture. We're looking at a reducing agent here. If oxidizing is gaining bonds to oxygen, what would you guys guess is reducing bonds to oxygen? Oh my gosh. Reducing bonds to oxygen is reduction. Yeah, there we go. Hey, it's late, ladies and gentlemen. I've been teaching all day. I apologize. Yeah, so what we're going to see here is if I take a molecule like this and I react it with lithium aluminum hydride, what we've done is we've taken the number of bonds to oxygen here, and we have reduced those bonds to oxygen. What kind of bonds have we replaced those with? Instead of bonds to oxygen, we've replaced them with bonds to hydrogen, right? So let's continue our mnemonic here. How might we recognize sodium borohydride and lithium aluminum hydride as great reducing reagents? Lots of bonds to hydrogen. Lots of source of hydride anions, right? Now notice, lithium aluminum hydride, it's a bit better. It reduces everything. Sodium borohydride reduces only ketones and aldehydes. That's a good fact to know. Lithium aluminum hydride is like the Mac Daddy of reducing reagents. When you see that, you know the MCAT is telling you super strong reducing reagents. A couple more questions. You guys know the drill. These questions 5 and 6 are going to be associated. Here you see sodium borohydride, so associated with the topics we just talked about. But let's take a look at our fourth learning goal, determining the effects of chemoselectivity. Again, we saw a great example of this right away. We said, and now we have a little bit more background about this, we said lithium aluminum hydride, Mac Daddy. I'm so upset that I picked that word to choose, but I'm stuck with it now. It's the Mac Daddy of reducing reagents, so it's going to reduce everything on this molecule. And I'm looking at this, and I'm a chemist, and I'm saying, wait a minute, I don't want to reduce this molecule, this part of the molecule. I only want to reduce this part of the molecule. So what I can do is I can react it with this ethylene glycol, this protective group, which forms a ketal, and that induces chemoselectivity, because now I'm going to see my lithium aluminum hydride does not react with this group. No reaction there. It only reacts with my desired group over here. That's a reasonably advanced application of this principle of chemoselectivity. What I want to look at are a few more fundamentals here. And what we're going to do is we're going to start out by taking a look at a sort of a warm-up to this. Again, this is review if you've seen it. Enolate anions. Let's take a look at this reaction. We see here these protons, normally carbon does not deprotonate. Normally, carbon does not carry a negative charge. And yet here we'll see that for a variety of good reasons, it will deprotonate. It will carry a negative charge. Why? What is special about that alpha carbon there that will allow it to deprotonate and carry a negative charge? Nice. Yeah, again, those twin factors of inductive and resonance, right? What we're seeing is the highly electronegative oxygen is pulling electron density away from that carbon-hydrogen bond, weakening that bond. And then after that hydrogen leaves, you guys see over here, resonance stabilization. So this is a great example of chemoselectivity because our base is going to attack this carbon specifically due to the favorable circumstances in that molecule. And again, you see the resonance stabilization here and the idea that we can carry a negative charge here because it's being resonance stabilized, right? Great example of chemoselectivity. Let's keep going here. We're going to take a look in just a minute at SN2 reactions. If I wanted to run an SN2 reaction, which carbon would my nucleophile prefer to attack, left or right? Nice. Yeah, we're going to be attacking the one on the right because of steric hindrance. The one on the left is going to be sterically hindered. The one on the right is going to be very susceptible to nucleophilic attack. Now, hang on to that. We'll come back to that idea in just a minute. Here's that protective group, right? The ethylene glycol protects the ketone, so the lithium aluminum hydride can't attack that ketone. And then what do? We apply some principles from earlier. We change the reaction conditions, protonate our leaving group. It pops off, and we have preserved our ketone group from beginning through to end, right? We're combining these ideas now, looking at the idea of chemoselectivity, the idea of varying the reaction conditions, and so on and so forth, okay? Our final learning goal tonight, we've got about 6 or 7 minutes for this. I want to take a look at some basic ideas of SN1 and SN2. Now, what we're going to see here is a great example of SN2. SN2. My question for you all is, what happens in an SN2 mechanism? Throw out some buzzwords for me. It's a one-step concerted event. Everything happens together. There's a backside attack mechanism. Yeah, we're going to see that it involves an inversion in configuration. And in fact, all of these ideas boil down to one fundamental step. The nucleophile has got to meet up with that electrophile and kick off that leaving group. So here we go. If you're not watching, watch for a second. We got a pretty neat animation here. There we go. We formed the intermediate, sort of pushed these around, and there is that inversion of stereochemistry, right? Now, when I look at this, the thing that jumps into my mind is that this is the exact plot of the movie Titanic, right? Think about it. Think about it. In the movie Titanic, it starts out with the dashing, you might say, electrifying Leonardo DiCaprio, right? This very attractive young specimen. I do say so myself. And also, it starts out with Kate Winslet in this relationship with Billy Zane, right? Cal, the bad guy. Yet their relationship is kind of this crummy, weak relationship. You might say they have a weak bond, right? Yeah? So what happens, right? She meets up with Leo. There's this instantaneous electrostatic attraction. They enter into this transition state where she's getting a little closer to Leo and kind of drifting away from Cal. And then what happens? Her and Leo form a bond. You know what I'm talking about? In the car, right? I got a little creepy there. And she kicks Cal out. See you later. See you later, right? But the key idea with this whole schema is that the movie Titanic does not happen unless Leo meets up with Kate, right? We need Kate and Leo to meet. Same thing here. My nucleophile has to meet up with my electrophile for this whole reaction to occur. Let's contrast that with SN1, right? When we think about SN1, what is the major event in SN1? We're going to end up with a racemic mixture, sure. We have a carbocation. The leaving group leaves. It's a two-step mechanism, right? But all of these ideas boil down to the fact that we have to form a carbocation, right? We have to form a carbocation. Take a look at this molecule here. What we're going to see is that bromine, he might just leave on his own. And let's think about this. What do you guys know about the stability of bromine in solution by himself? Third time I've asked this question tonight. You see, these ideas start repeating themselves. Pretty stable, very happy, right? He's going to just get out of here, whatever, right? Also, take a look at our carbocation. Now, we said carbocations don't often like to form, but why would this carbocation be a little bit more stable than your standard carbocation? It's tertiary. Those methyl groups are going to stabilize that guy, right? So I like to think SN1 is the movie Titanic if they had cast Beyonce in the role of the lead chick. I can't remember her name right now, right? Because she would have been like, look, I'm a single lady, I'm an independent woman, everything you own in a box to the left, get out of here, I'm going to go be single all by myself, which leaves her then susceptible to nucleophilic attack of her own. Now, again, I know I'm kind of being silly here, gang, but there's a good reason for that, right? Look at this reactant and tell me, why would this be terrible for an SN2 reaction? SN2 is all about nucleophile meeting up with an electrophile. If I have a nucleophile here, my nucleophile is going to want to get at that electrophile, but it's not going to happen because of steric hindrance. At the same time, the very factors that make this bad for SN2 make it great for SN1 because those R groups are going to come along and stabilize my intermediate. So keep this in mind. The key step in SN2 is nucleophile meets electrophile, and literally any condition that helps nucleophile meet electrophile, that's going to help SN2. The key step in SN1 is that we are going to be forming an intermediate, and in fact, this explains literally everything about this, right? Because you guys said racemic mixture for SN1. What about that carbocation is going to induce a racemic mixture after the nucleophile attacks? Why would that guy be susceptible to racemization? It can be attacked from both ways. And again, I don't know who made these animations. They know how to make this stuff way better than I do. Watch this. This is really neat. We're going to take that guy, we're going to convert it into a vector object, and then we're going to flatten it out in space to show that the nucleophile can attack from top or bottom. How freaking cool is that? How freaking cool is that? Let me ask you guys one more question. I want to walk away with this, with one more trick the MCAT can throw at you. Homeboy here can attack from top or bottom. Still not going to get a racemic mixture. Why not? Yeah, the product is not formed. So this has become such like an automatic thing amongst my students. I want you guys to be very careful with this. If a chiral product is formed, only then do you get racemization. I've seen MCAT questions where they don't make a chiral product, and you got to watch out for that, okay? So that is our time together tonight, ladies and gentlemen. You know the drill. You've got some practice questions to work on. I will tell you, if you do none of these practice questions, except for one, this is the question to do. It is the best organic chemistry question I've ever seen in the topic of SN1, SN2. You will get it wrong, is my prediction. Actually, mathematically, about a fifth of you will get it right. But you will learn something from the mistakes that you've made, okay? With that in mind, I'm going to cut, yes, sorry to be real with you, Emily, but it's a good question as a learning opportunity. I'm going to cut here, guys. You were wonderful tonight and earlier on. Thanks so much for coming out. I'll see you in future channel sessions. It's the Mac Daddy of questions, Will. That's right. Bye, everybody. Thanks so much. Have a great evening, and we'll see you in